the kernel for that.
Excellent. Okay, so we are live. And, all right,
So this is how it works.
this is how it works. So our last talk of the day is going to be Tom. He's going to talk about the PNS router, which is obviously one of the core sections of KiCad. And take it away, Tom.
Yeah, thank you, Seth. So yeah, my name is Tom Wostowski. I'm the original author of the push and shove router for KiCad. It's been pretty much 10 years since it was there. I kind of have to recall a lot of stuff in order to make this presentation because I forgot for myself how it works. So I'll try to share what I discovered about the router with you, just in the case you wanted to contribute something to it. It's a rather complex beast. Probably if I were to write it like today, I will design it a bit differently, but yeah, we have to live with what we got. So I will first talk about how we store the geometry and index the items in the router so that the routing algorithms like shove, walk around, dragging can efficiently work on them. Then a little bit about the algorithms themselves, but not about their inner workings, but how they are integrated in the class hierarchy. I'll be probably switching between the code editor and then this presentation repeatedly just to show you some relevant points in the code. Then there is a tool that lets you analyze the behavior of the router. It's very badly documented. So I hope with this presentation I'll provide you with some info how to use it, because this tool lets you study the router operation step by step with a lot of extra debugging information. So it's an invaluable tool for learning and reproducing issues. And then, if time permits, we will try to add a new dragging algorithm. And I will show you what needs to be changed in the router step by step. In order to have it, the example being a dragging algorithm for multiple traces. Great. So every program operating on some items requires a storage model. So in the KiCad router, we don't use the class board or board items directly because they were not meant for fast indexing and topological queries. So the shove and walk around algorithms, which are the cornerstone of the push and shove router, do a lot of collision searching. So we needed more spatial indexing, which in our case is based on R3s. Then we need to be able to assemble entities that belong to the board, be that segments, vias, arcs, etc., into chains. The chains are called lines in router parlance, and they have to be assembled on the fly. So imagine, you have a line that collides with another one. The router does not operate in the concept of lines directly. Instead, it's a set of loose segments, vias, geometric shapes that are on the fly assembled into connected sets of items and then processed by the shoving algorithms. We also do a little bit of custom memory management, in particular, or lightweight of the copy and write mechanism, so that we can try different optimization scenarios and revert the changes in the case of a failure. And all of this is interfaced with host KiCad environment through a special class. So this router can be integrated into other EDA tools. I think Horizon is still using it. So let's start with the geometry primitives. So the very basic class for representing each piece of board geometry is simply called item. This all belongs to a PNS namespace. I just didn't prefix them for the clarity of the drawings. Items themselves are derived from some memory management primitives, but this is not super important for this presentation. So We have different kinds of items representing the geometry. That is solids, which are used to represent paths, keepouts, and in general, items that cannot be deformed by the router. I mean, the router is about deforming, modifying the shapes of traces, moving vias, but keeps the paths and rule areas, such as keep-out areas, unchanged. Then segments and arcs that can be composed together into lines, following their connectivity. And of course, they can be deformed by the show or walk-around algorithms. Then we have vias and v-vias. The first one is a physical via, representing a via. The second is a virtual one, which is not really a via, and it doesn't have a hole. It's used to fan out multiple traces, especially of different widths. So imagine you have this trace had a junction here with another one. There would be a virtual via in the storage model here. This is mostly used for shoving and dragging traces which have width transitions, and sort of a hack. Now, another class that is very relevant is a joint class. Joint is a point with a layer range attached, and these joints are hashed and are added to a special hash for each endpoint or anchor point of the other items. Then, if you want to follow the connectivity of particular objects, all you need to do is to do a quick constant time hash lookup for the relevant joints and build the connected set from the matching items. All of this is stored in a container called node. What else? The basic assumption here, which is violated in some places, mea culpa, is that items are non-mutable. Means if an item is owned by a node, in order to modify it, you have to remove the old one, clone it, modify it in any way you want, then add to the node. You cannot modify items that belong to a particular node container. So yeah, the connectivity, as I already mentioned, we have a flat connectivity model. Items do not know about each other. It's the node and joints that bind them together. There is a hash table, and each joint internally has a list of items linking to it, so that you can do a linear time connectivity graph traversal and build all these, traces or other geometries. These joints are somewhat of an internal feature of the router. I mean, they are usually not accessed by the user. It's the node that manages them inside. Well, then the container that we have, the node, has another feature. Since we imagine you have a large core. You want to show, you are dragging a trace and it collides with another trace, right? We attempt at showing it. This is a relatively minor modification. It affects, like, let's say 20 out of 100,000 entities. And we must have some sort of revert mechanism in the case the algorithm has failed, either at computing the shoved traces or failing at the optimization, lossing cleanup. So there is a concept in the node of branches, which is a lightweight copy on the copy on write mechanism. So imagine the bulk of geometry is stored in a root node. Then you can create branches. They can be either linear, like one branch derived from another, or tree-like. And each branch keeps only the items modified with respect to the root node. So there is no need to copy the entire data model just because you want to do a simple change. Furthermore, you can keep several nodes in parallel and, for instance, try a different optimization algorithm on each of them, pick the best one, and then commit the changes from your branch that from a selected branch back to the root node and further back to the host KiCad board object. Yeah, so there are two methods that are extremely important. One is called node branch that creates a derivative branch of a particular node, and a commit method that basically takes all the modifications from a particular branch, pushes them to the root, and further through the integration code with the KiCad host data model to the board structure. So I mentioned the line object, which binds together several geometric primitives into something that looks like a trace. So in our router, it's a single layer, single width trace that can consist of segments and arcs of altogether of the same width. So here we have some sort of a more complex trace that consists of 4 lines. This is 4 segments, front copper, 6 segments back copper, and then another one with a bunch of segments. But it's considered a separate line because it has a different width. The function that follows the connectivity and creates all this on the fly is called assemble line. That's also an important entry point when you want to contribute something to the router. So, an example how to change the width of a line that contains a given segment. Usually you select a particular segment and then you have to get all the connected items in the same layer, forming a line, modify, and apply. So, first of all, board contains our board geometry, except not in class board, but in the PNS node structure. Seg argument is the first segment we want to start changing the width of an entire line from, and well, new width is obvious. So first of all, we begin with creating a branch. It is possible to change, the root node directly, but you lose the capability of notifying the host classes such as the view, controller, etc. So I would not do that. Always branch before modifying something. So yeah, we create a new branch of the node. We clone the original segment. We change its width to a new one. Then remove the old, add the new. These are not mutable. I mean, you cannot just if this segment belongs already to some node, you cannot change its properties. You must remove it, replace it with a new one. And if we are happy with our modifications, we call commit. This will apply all the changes from the node you just created back into the root node and update all the relevant structures in KiCad. Yes?
So the branch function there, it stores a reference to the old node in the new node, or does it know where to commit to?
Well, board is your root node.
Mm-hmm. Mm-hmm.
Branch is a branch of your board.
Mm-hmm.
Branch is a branch of your board.
Mm-hmm. But it doesn't know what it's a branch of.
It knows it.
It creates it.
Well, the branch method, node colon branch, basically creates a child node of the node being branched. So internally, the node class knows its parent node, and it also manages its set of descendant child nodes. So yeah, just a reminder, no in-place modifications. So remove, modify, add new. And the benefit of this commits and branch-based system is that if you screw something up, broke the geometry, all you need to do is to not call, not commit, and this will all get discarded, freed up, as if it never happened. So, the class that puts it all together, and it's an entry point, is called PNS router. It's a thing obvious. And it's an entry point for all router operations. So we have this paradigm of start, move, fix route. These are three methods in the PNS router class. The first one, start routing. Well, tells the router to begin routing, right? You can either start at an arbitrary point or at a particular item. Like imagine you're starting a trace on an already existing pad or in the middle of an already existing trace. Then you can repeatedly call move. This is normally called from the KiCad host tool every time you move the mouse, right? It just feeds these mouse events and the router updates its state, updates the state of the push and shove algorithms, etc. Once you're happy with what you've just thrown, you call fix route. This will finalize the particular trace. It will commit it to the root node of that contains the whole board geometry. But in order for it to be moved, to be forwarded to the actual board object, which belongs to PCB-new, don't forget about commit routing. So how does the router communicate with KiCad itself? Because it's a kind of a self-contained piece of code, mainly for testing and also for historical reasons. There's another EDA tool that depends on it. So the router does not use directly any KiCad types except for the geometry. But instead it uses some sort of a proxy class. We call it PNS KiCad iFace that performs several functions. So for the most important is translation between KiCad's classes, such as via, track, etc., into PNS items. So it provides four methods worth looking at. Sync word is basically what takes the board object from KiCad and generates all these PNS specific primitives, puts them in the relevant node structure, indexes them, etc. Then add item, remove item, update item. They tell PCB-new that the router has done something to the native PCB-new primitives. So if you change the PNS segment, or this segment will have its board item created by add item or update item and propagated to the host model, to the host PCB-new model. Some more functionality of this interface class. It triggers view updates, so when you move things around, it notifies that, oh, this and that piece of geometry changed its appearance, so you have to redraw it on the screen. It provides some debugging capability, so you can draw transient debugging graphics, emit debugging messages. This is very useful for analyzing how the router works and fixing bugs. And last but not least, this interface class provides constraint resolution. So you can ask for an object called rule resolver, and this rule resolver will get you things such as clearances between different sets of objects, trace widths, differential pair gaps, keep out properties. But I think, the intestines of this are way beyond the scope of this presentation. So, forgive my shitty drawing skills. I'm not a UML expert. So this is more or less a class hierarchy as far as the router and its integration in KiCad is concerned. So the entry point on the KiCad side is called router tool. It's a derivative of an interactive tool class. The tool framework was presented by Ein. So for the So, well, you can ask him for the details of how the tool framework works. Then the main entry point in the router tool itself is main loop, which basically processes the events like clicking on traces, moving, etc., forwards them to the actual routing engine. Then the router, depending on the operation, creates an object for a particular algorithm. We have several ones I will show later. And through the PNS KiCad iFace class, it updates the view, updates the board, and also fetches the modifications on the board and gets the relevant design rules. So we have several dragging and placement algorithms, and they follow the same pattern. So start, routing, or dragging, move, fix, then commit. They are split into two categories. So placement algorithms create new lines, new tracks. So we have a single line placer, differential pair placer, meander placer for the accordions. We have a differential pair meander placer for meandering differential pairs, and then we have a bunch of dragging algorithms. So there is a basic dragger for single tracks, and a component dragger which can take a bunch of components and move them with the traces attached. We will try, I will show you a very primitive dragging algorithm for dragging multiple traces together as an example of how to add a new feature to the router. Okay, one more thing. Before you start experimenting, I really suggest that you build the PNS debug tool. This is an obscure tool, poorly documented, shittily written, beware the code is ugly, but it's very useful for understanding the router's behavior. It lives in QA tools PNS directory. You must enable a particular build flag in CMake in order to build it, and enable a particular flag in advanced config for it to have some data to feed on. So let me show you an example. Let's open PCB new with some board. Say we have a trace here. Let's try routing something. With this enable router dump option enabled in advanced config, when you press 0, it will ask you if you want to save a complete dump of the router state into a file, including all the past events during the current routing session, so that then you can replay them and analyze them offline with a lot of debugging data and messages. So let's do OK. We then close PCB new and launch the debug tool. The syntax is replay and the name of the log file. But by default, the logs are stored in a bunch of files called PNS dump, PNS KiCad project rules, KiCad project, the log with the events and the settings of the router. Also, reporting bugs for the router is very easy through this mechanism, because all you have to do is reproduce your bug, press 0, and send these log files to us if you want the bug to be fixed quickly. Beware, because it dumps the entire geometry of your board. So if there is something like secretive or NDA, this will leak your private data. So let's try the debugger tool. Without what?
You can do it without giving it the file, you just do a file open.
Really? I didn't even know. But it stopped working. Perhaps I'll have to recompile my kernel to fix this.
Wait, it's trying to load PNS.1 as a file exist.
But it worked, 10 minutes ago. Okay. Maybe the master one will work. Except that it's not the right log.
It's your data, it's not.
I think it's just I made a very complex change, and with a lot of debug craft, it's just taking too much time. So let's make a simpler one. Just show me one trace, 0, save the log. Yeah, there we go. So this shows an annotated view of your board with a lot of additional debug stuff. By default, it's all on, so you see this rubbish of labels. Now, what's very useful here is you can replay the routing operation with a granularity of a single motion event. So, for instance, if the router at certain point refuses to do something for you, you can save the transient state by pressing 0 and then study it iteration by iteration, also with a lot of extra graphics left for debugging. So here we have.
You have to do special compile to get to say by script 0.
Yes, you have to compile this debug tool.
No, just to save it.
And to save it, you have to enable it.
Advanced config file.
Yeah.
But you can do that on the release KiCad.
Is there a good reason not to have it enabled, always enabled? It blinks all the data.
Yeah.
Only if you save.
I think if you accidentally hit the zero key,
Well, it saves to your project directory where everything is animated.
but if you accidentally hit the key, it will do that in the background, and that takes up a fair chunk of it. It'll dump everything out. So,
But there's no runtime cost. There is a massive.
Runtime cost is 0.
runtime cost for listening for the key is 0. Runtime cost for dumping the data is very much.
And it's right next to your tuning stuff, so it's very easy. I don't have zero. I do, but
Nix doesn't use 0.
Yeah, I don't know if we have a hotkey attached to it. Probably we don't, because this is an obscure feature, used by us internally for debugging. So the panel here basically contains all the debug information generated by the router in the hierarchical way. You can also have a look where each of these debug messages were generated, file and method, and the relevant line, which is helpful for learning the code flow, the operation of the router. It's not simple, and quite frankly, kind kind of even I don't know how it really works after so many years. So here, for example, we have the show algorithm at work. It works iteratively. So first, it looks for the first colliding segment. Then it assembles the colliding path and processes it segment by segment until by selecting the primitives you can basically observe all of them and analyze how it works. Is there anything else to?
So the line there is from the source, or?
Which
in
one?
The bottom
The
it says file method line,
yes,
and this is from the source when it was compiled.
yes, exactly. Give me a moment. Yeah. So there is a macro called PNS debug that you can place inline in the router code pretty much anywhere in order to emit messages and emit geometry items with some annotations for analysis and debugging purposes. Where was it?
Presumably this changes when you change the code. So is it possible to find out like what you commit this was from?
No,
Okay, so you just need to know what.
that wasn't my intention. This is for reproducing bugs and sometimes adding some extra debugging information in a graphical form to understand why the router behaves in this or that way. This is not for the purpose of, like long-term traceability of the bugs. This is what it is for.
No, I'm not talking about that. I'm talking about like if the file is changed in between, is it possible to see like when this was compiled?
No. You must build the exact. If you want this tool to reproduce down to the bug the router behavior, you must compile it from the same commit as the version of KiCad that was used to generate the dump.
Which you get from the.
Which you get from the
version block on the GitHub or the GitLab issue, right?
Okay, yeah, but it's not in the file, so if you just have a trace file, you can actually. That's why you
Yeah, well, if you have a trace file, you hopefully either got it from a machine that you know what commit you're running, or you got it from a user who opened a bug report with the right version info.
Yeah.
So an example an example of such a debug call somewhere in the show algorithm. So this is handled by a very ugly macro, but the macro is unfortunately needed in order to attach the file line and file name and position information. So it takes the decorator object, which is mixed into many PNS classes, in particular all the placement and drag algos. So you pass it here. Then you can either add a shape or add an item. Add shape takes a raw KiCad geometry item. In this case, it's a shape rect, and you can override the color, width, and attach some sort of a label that will be later displayed in this hierarchical tree panel with the dump of all the items, so that you can know what generated a particular debug item. You can also add PNS items directly, like here. In this case, obstacle seg is just a PNS segment. And they will all appear with labels, annotations for your debugging convenience. You can also generate asynchronous messages without any geometry attached through a message methods in the debug decorator. Then any sort of formatting just accepts a plain VX string. You can use VX string format in order to compose more complex messages. So would you like to see a sample implementation of a dragging algorithm for multiple traces? And all right, this will be a bit random, probably more random than disorganized than what I have presented so far. Nevertheless, let's try. I will push that branch when I'm confident it works, and I will comment it a little bit further so that sorry, lack of sleep, so that it can serve as an example for whoever wants to improve or add some new features to the router. So we start by creating a new algorithm class. I called it multi-dragger. Now we need the code editor again. So we create a new class. We derive it from an abstract dragging algorithm, and of course we have to provide certain methods: start, drag, fix. These are the most important ones. The rest is more or less boilerplate. So let's focus on the three basic methods of each dragging algorithm. So the start takes a set of primitives to drag. In our case, it's a set of segments for the moment. So for each of them, we try to assemble a complete line. That means a track of a fixed width on the same layer. We also do a little bit of redundant item pruning here, because you can imagine the case the user has selected like two segments belonging to the same line. So they must be removed to form so that they don't no multiple lines are created, because this will confuse the router. Then we perform some initial geometry stuff, like figuring out which is the line that is attached to the cursor, so that we can use it as a reference and move all the neighboring lines accordingly. This is just some geometry mumbo jumbo. And in case we didn't find any, we cannot really continue dragging, because we have no idea where to attach the cursor to. So the start method, if it returns true, it means yes, success, we can continue feeding the events to drag. Otherwise, we abort. Then the drag method. So first of all, it creates a new branch, because we cannot modify anything in the router storage model without branching first. Then we go through all these lines that we created a priori in the start dragging methods, do some math on them. It's for the moment irrelevant. I mean, the algorithms that I'm showing here is very crude, but what's important is you remove the original line and replace it with a copy of it which has modified geometry. And there is some more geometry stuff that is not super relevant. Also, I added some debugging calls so that I can replay it step by step in this in the PNS debug tool, in order to figure out what's wrong in case it's not working the way I want it to. The last thing is fixed route. which is very simple. We keep the status, whether the last iteration, the last call to drag or drag has been successful in a private field of the multi-dragger class. Do a sanity check, and if everything went okay, we call commit. This will trigger the router to actually take the changing. Went okay, we call commit. This will trigger the router to actually take the changes done by the multi-drag algorithm into account, propagate them to whatever is necessary, update all the KiCad views, update the host storage model, etc. So this is as far as the drag algorithm is concerned, but it's not only about creating a new placement algorithm or dragging algorithm class to have it working. So the next part is integrating it in the PNS router class and the router tool. This is a bit more, this is a bit trickier. I tried to, in that multi-drag branch, I will really publish it as soon as possible, as soon as I have this code more or less working, cleaned up. I'll try to make the commits very atomic, so that each commit shows like one step of modification to router. So, integrate multi-dragger in the PNS router class. Maybe we could do this using a diff tool. So let's take the commit ID. So the entry point for all dragging operations in our is router start dragging. Accepts the point where we begin, a set of items to be dragged, and also some other parameters that are not super relevant as of now. So before we had a simple single line dragger and a component dragger. So we check what sort of items are in the set of items we wish to drag. If there are only solids, that means component paths, we create a polymorphic object of component dragger type, let it do the job. If there is more than one track or arc segment in the item set to drag, we create our new multi-dragger object. Otherwise, if it's a single thing, we go with a single trace mode. I don't think anything else requires to be modified as far as the router itself is concerned. But for the router tool, we had to do a bit of hackery, which is not very clean for the moment, but nonetheless, let's try going through it. So we had to cater for sanitizing the set of items that has been selected. Before we only handled single items. Now we must handle more of them. Can inline drag is a method that tells KiCad tool framework and the edit tool selection tool that a particular item can be dragged through the PNS. Then, yes, we need to handle where we have multiple items we want to drag. So we go through the selection, we find the parent objects, we check the types. We can start dragging on a segment, arc, or a via. We assembled a set of items to pass to the router. And then the rest of the code, I don't think it requires any particular modification. Okay, I think that's all that I've prepared for today. I'll be happy to answer your questions. Sorry for the lack of organization here and lack of structure. But as I said, I haven't been too active on the router front until recently, and I'm myself recalling how it really works inside, as well as other subsystems of KiCad.
So does this actually work?
Yeah. It's a remarkably shitty algorithm, but but it works. Yeah. So this is the log viewer.
You already released that. Is that intentional?
I think so. But so far it has very limited functionality, so we need a bunch of loose traces that have dangling ends, because dragging the bodies of multiple traces is not implemented. So let's get rid of these vias, and then select a bunch of traces, then press D.
You might be in the wrong branch.
Now this is release dev. So are we there? Tom multi-drag, release. Okay. No, it should be fine. Okay, let's draw into traces. Sorry? These are graphical lines. Mea culpa. It looks like I broke something. You see? Because it should be triggering the drag operation. For some reason, it's not doing this.
So is there any way to debug why it's?
No, multi-drag triggered, start 2 items. Oh, you see? It's just probably not handling all the cases correctly, and the algorithm is pretty terrible. I mean, it should ensure some clearances and parallelism of the traces, but I did it as a demo for another developer who was willing to contribute this multi-drag algorithm. In the end, I don't know what's the status of his modification. We'll have to talk, or I will finish it myself. Yeah, so this is more or less how it works. Maybe we can do that on a larger board. It's probably a bit picky about the directions of these dangling segments. Yeah. Yeah, and I think the cursor must be placed on. Yeah, you see. So it tries to keep them parallel. Of course, it fails at in certain under certain conditions, and this is not, such edge cases are not handled yet.
So the highlighting for conditions, is that implemented in there, or is that?
No, highlighting is a function of the router. You don't need to worry about it in your placement algorithm. The shove and walk around, that's a different subject, but I don't think we have the time, and I would have to, quite frankly, recall really how the shove algorithm works inside out in order to teach others about its operation. Yeah, so thanks again.
Thanks, Tom. Okay, now that we're all
experience.
There's a tag in GitLab specifying all the router bugs, so you can find all the interesting corner cases that still need work in the router.
Yes,
right.
remember.
Thanks for joining us.
And the zero key is reference.